At the center of our Milky Way galaxy lies something so mysterious, so extreme, that it defies everything we thought we knew about space. Invisible to our eyes, yet influencing the movement of stars, bending light, and perhaps even shaping time itself, it has become one of the most captivating enigmas of modern science. Astronomers call it Sagittarius A star, but to those who dare to ponder its secrets, it's something far more profound: the beating, invisible heart of our cosmic home. What lies inside? Is it a void, a singularity, or perhaps something far stranger, something that hints at deeper laws of reality? To begin understanding what might lie inside the black hole at the center of our galaxy, we must first understand what led us here. Our story begins not with the black hole itself, but with light, specifically, light that wasn't behaving the way it should. In the early 20th century, astronomers observing the core of the Milky Way noticed strange behavior in the orbits of stars. These stars, located near the galactic center, were moving far too quickly, as if being slingshot by some invisible force. At first, the assumption was simple. There had to be an object of massive mass hidden in the darkness. But the data didn't add up. There wasn't any visible matter accounting for that kind of gravitational pull. No cluster of stars, no supernova remnant, nothing, just darkness. It wasn't until the late 1990s and early 2000s, with the advent of more precise infrared and radio telescopes, that things began to change. Teams like Reinhard Genzel's group at the Max Planck Institute and Andrea Ghe's team at UCLA began charting the paths of individual stars orbiting the galactic center. They weren't just speeding, they were whipping around an invisible point with dizzying velocity. One particular star, known as S2, completed an elliptical orbit in just over 16 years, so fast and so close to the center that the only explanation was a compact object with a mass over 4 million times that of our Sun. This, then, was Sagittarius A star, a supermassive black hole, so dense, so gravitationally powerful, that even light could not escape its grip. But no one had ever seen it directly. The region surrounding Sagittarius A* is among the most chaotic in our galaxy. Clouds of gas and dust swirl in turbulent eddies. Electromagnetic storms rage. Radio waves pulse out from what seems like nowhere. In this maelstrom of cosmic noise, the black hole itself sits silent, invisible, not because it's hiding, but because it absorbs all signals, all light, all meaning. To find it, astronomers relied on indirect evidence. They studied the radiation emitted from the accretion disk, a spinning cloud of matter heated to millions of degrees as it spiraled inward. They measured the X-rays flaring out from time to time, like whispers from an otherwise silent entity. Every flare, every orbit, every pulse was a clue, a thread in a massive puzzle we were only beginning to assemble. In 2019, that puzzle took a dramatic turn. The Event Horizon Telescope, a network of radio observatories spanning the globe, released the first ever image of a black hole, not Sagittarius A*, but its cousin, located in the galaxy M87. It was a glowing ring of light surrounding a dark shadow. That shadow wasn't the black hole itself. It was the event horizon, the point of no return. What lay beyond that horizon remained hidden. And yet, the image changed everything. For the first time, humanity had visual proof of something we had only theorized for decades. The M87 black hole became a benchmark, a proof of concept. It proved that our methods could work, and it lit a fire under the scientific community to turn those methods toward our own galactic core. But here's the problem. Sagittarius A* is different. It's smaller, it changes faster, and it's cloaked in dense cosmic fog. Where M87's black hole offered a relatively stable target, Sagittarius A* flickers like a candle in a storm. Images blur, data gets scrambled, and every attempt to capture a coherent picture of it feels like chasing a ghost in a whirlwind. Still, the attempts continued. Observatories around the world collaborated. Algorithms were refined. Observational time was extended. And in 2022, the Event Horizon Telescope delivered again, an image, this time of Sagittarius A* itself. It was less crisp, more elusive than the M87 image, but it was real. It confirmed our models. And most importantly, It gave us a direct look at the shadow cast by the most powerful object in our galactic neighborhood. But here's where things get strange. Despite its size and power, Sagittarius A* doesn't behave entirely as predicted. Its flares are unpredictable. Its accretion patterns don't always follow expected paths. And then there's the issue of the matter that surrounds it. Instead of being drawn in rapidly, a surprising amount of matter seems to hover near the event horizon, undecided, as if paused in a cosmic hesitation. This raised questions. Could there be unknown physics at play? Were we misunderstanding how gravity works in extreme environments? Or was Sagittarius A* hiding something even more complex than we imagined? To answer these questions, researchers turned to simulations. Massive supercomputers ran equations based on Einstein's general relativity, modeling how matter and light behave near an event horizon. The results were eerie. The simulations matched reality, mostly, but every so often, anomalies appeared. Light bending in ways it shouldn't. Time dilation affecting regions too distant to explain. Gravitational echoes, strange reverberations in data, suggesting that perhaps, inside the black hole, something was reflecting energy back out. That shouldn't happen. Not if the black hole is truly a one-way street. And so the mystery deepened. Could there be structure inside the event horizon? Some scientists speculated about fuzzballs, an alternative to singularities, where matter doesn't collapse to an infinite point but forms a tangled quantum web. Others suggested that black holes might contain holographic imprints of the universe, a kind of cosmic memory storage. But such theories, while tantalizing, remain unproven. What we do know is this: Sagittarius A* is not just a gravitational pit. It's an active, dynamic entity, shaping the galactic environment, influencing stellar formation, and perhaps playing a role in the very fabric of our galaxy's existence. And yet, with every discovery, new questions arise. What caused the periodic X-ray flares seen by NASA's Chandra Observatory? Why do some stars pass dangerously close to the black hole and yet survive, when by all accounts, they should be torn apart? What is the nature of the G objects, clouds of gas that orbit the black hole like stars, but don't behave like anything we've seen before? These puzzles point to something deeper, something more fundamental. Not just about Sagittarius A*, but about black holes in general. About the nature of information, of time, of reality itself. And as we delve deeper into the heart of the galaxy, we are reminded of an ancient truth. Sometimes, the most profound knowledge begins where light ends. In silence, in shadow, and in the gravitational pull of a mystery that refuses to let go. To truly grasp the nature of the black hole at the center of our galaxy, one must first come to terms with what a black hole truly is, not in metaphor, but in physics. A black hole is not a place. It is not a thing. It is a boundary in space-time, a region where gravity has grown so intense, so consuming, that not even light can escape it. It is, quite literally, the collapse of space into itself. And what lies at its heart is a question that physics has been chasing for decades. The story begins with the collapse of a star. When a massive star runs out of nuclear fuel, its core succumbs to gravity. If the mass is great enough, not even the pressure from degenerate matter, particles crushed so tightly they resist further compression, can hold it up. The core implodes. In this implosion, the fabric of space-time folds inward, creating a singularity, a point of infinite density and zero volume. Or so the theory goes. Einstein's general theory of relativity predicts this collapse. But the equations also predict something strange at the boundary surrounding the singularity, the event horizon. This isn't a surface in the traditional sense. It's a mathematical boundary, a one-way gate. Once anything passes this limit, it can never return. Not a spaceship, not a particle, not even information. It is the ultimate curtain. And at the center of the Milky Way, Sagittarius A* is the stage behind that curtain. But there's a problem. While general relativity predicts the event horizon and singularity, quantum mechanics, the other pillar of modern physics, doesn't quite agree. According to quantum theory, information cannot simply vanish. This sets the stage for one of the most perplexing conflicts in science, the black hole information paradox. When matter falls into a black hole, does its information, its quantum signature, vanish forever? If so, this violates one of the most sacred rules in physics. But if the information somehow survives, where does it go? Stephen Hawking entered this debate in the 1970s with a radical proposal. Black holes aren't entirely black. They emit radiation due to quantum effects near the event horizon, what we now call Hawking radiation. Over time, this radiation causes the black hole to lose mass and eventually evaporate. But Hawking's own model suggested that the information would be lost with the black hole's evaporation, creating a paradox that still fuels heated debate among physicists. Sagittarius A* is no small black hole. With a mass of roughly 4 million suns, its gravitational grip extends for light years. Surrounding it is a region known as the accretion disk, a swirling inferno of matter spiraling inward, heated to millions of degrees. This disk shines in X-rays, visible to telescopes like Chandra and NuStar. But the light doesn't come from within the black hole. It comes from the death throes of matter on the edge of oblivion. Inside the event horizon, we cannot see, not because it is dark, but because the rules we depend on cease to operate. Space folds. Time distorts. In fact, near the event horizon, time slows relative to the outside world. From an observer's perspective, anything falling in appears to slow to a crawl, asymptotically approaching the edge but never quite crossing it. But this is only from the outside. From the viewpoint of the falling object, the experience is different. They fall freely, unaware of the boundary, until gravity compresses them toward the singularity in an unimaginable final moment. Theoretical physicists have tried to peer deeper into this descent. Some describe a process known as spaghettification, a colorful term for what happens when gravity stretches an object lengthwise and compresses it sideways. The tidal forces become so extreme that, long before reaching the singularity, the object is torn atom from atom, molecule from molecule. Not metaphorically, literally. The strength of this tidal force depends on the mass of the black hole. Paradoxically, the larger the black hole, the gentler this process is near the event horizon. For Sagittarius A*, it's believed that someone could pass through the event horizon without immediate destruction, though what happens afterward remains unknown. What is known is this: once inside, there is no coming back. The laws of causality are broken. The arrow of time points inward. The very notion of space becomes distorted. The singularity isn't a point in space, it's a point in time, a future all objects inside the black hole must eventually reach. And yet, for all its ferocity, Sagittarius A* is unusually quiet. Unlike the actively feeding black holes in other galaxies that blaze with radiation as they devour matter, Sagittarius A* seems to be starving. Astronomers have long puzzled over this. Why isn't it brighter? Why isn't it consuming more? Some believe it's simply in a dormant state, a sleeping giant between meals. Others suggest that it may be consuming matter more efficiently than expected, with less radiant energy escaping. Or perhaps it's surrounded by magnetic fields so intense they suppress the emission of light. In 2013, NASA observed a cloud of gas, dubbed G2, approaching Sagittarius A star. Scientists expected a show. As G2 neared the event horizon, it should have been ripped apart, flaring brilliantly in X-ray and infrared wavelengths. But the fireworks never came. G2 passed near the black hole and survived. How? No one knows for sure. Later analysis suggested G2 might not be a gas cloud at all. Some believe it's the bloated atmosphere of a faint binary star system. Others propose it might be part of a class of strange, dust-enshrouded objects orbiting the black hole, neither entirely gaseous nor stellar, but something in between. These uncertainties highlight a deeper truth. Despite knowing so much about black holes in theory, we know so little in practice. We can model their behavior. We can detect their influence, but we cannot see inside. And so we return to the shadow. The shadow of Sagittarius A* isn't a literal darkness. It's a silhouette cast by the bending of light around the event horizon. When the Event Horizon Telescope imaged it, the result was a blurry ring of emission, distorted by the intense gravitational lensing of space-time. This ring tells us the size of the event horizon. It confirms Einstein's equations, but it doesn't reveal the interior. To know what lies inside, we must leave known physics behind. Some theories propose that the singularity is a gateway, a tunnel through space-time known as a wormhole. Others suggest that the black hole contains a Planck star, a hypothetical core where quantum gravity prevents total collapse. Still others propose that the singularity is not real at all, that it's a mathematical artifact pointing to our incomplete understanding of gravity at the smallest scales. Whatever the truth, one fact remains. Sagittarius A* is not just a cosmic vacuum cleaner. It is a frontier, a boundary between what we know and what we cannot yet explain. A reminder that the universe still holds secrets we are only beginning to uncover. And perhaps, deep within its unseen depths, it holds a piece of the puzzle we call reality. In our efforts to unravel the secrets hidden within Sagittarius A*, we have been forced to confront the limitations of human vision, both literal and conceptual. What do you do when the object of your study cannot be seen? When it swallows not only light, but information? The answer lies in collaboration, innovation, and patience, the kind that spans continents and decades. To peer into the abyss, scientists have constructed the most ambitious astronomical instruments ever devised. And in the heart of that effort stands the Event Horizon Telescope. The Event Horizon Telescope, or EHT, is not a single telescope, but a global array of radio observatories linked together to form a virtual Earth-sized dish. The technique is called Very Long Baseline Interferometry. When multiple telescopes separated by thousands of kilometers observe the same object at the same time, their data can be synchronized and combined to produce images with incredibly high resolution, sharp enough to detect the silhouette of a black hole. It took years of planning. Observatories across the globe, from Hawaii's Mauna Kea to the South Pole, coordinated their efforts with atomic clock precision. Hundreds of terabytes of data were recorded on hard drives and flown to supercomputing centers for processing. The goal? To capture the shadow of Sagittarius A*, and finally glimpse the shape of gravity's ultimate prison. But Sagittarius A* is a challenging target. Unlike the black hole in Galaxy M87, which is more stable and slow-changing, Sagittarius A* flickers rapidly, its light patterns changing over minutes instead of days. The image is like trying to photograph a campfire during a hurricane, with shifting winds and swirling embers obscuring the view. To overcome this, scientists used computational imaging techniques that reconstructed the image from blurred, incomplete data. The result was not a single snapshot, but a statistically averaged image, a composite that reveals the most persistent features of the black hole's behavior. When the EHT team released the image in 2022, it was the culmination of more than 2 decades of work. There it was, a faint, glowing ring surrounding a dark center, the gravitational shadow of Sagittarius A*. The ring glowed in radio wavelengths, emitted by particles heated near the event horizon. The dark center wasn't the black hole itself, but the absence of light, the place where everything disappears. But seeing the shadow is only the beginning. It is not a map. It is a silhouette, a clue, not a conclusion. To go further, we must lean on theory, simulation, and deduction. This is where general relativity meets numerical astrophysics. Scientists input known laws into simulations, Einstein's equations, Maxwell's equations for electromagnetism, quantum corrections, and watch how matter behaves near a black hole. These simulations can take weeks to run on supercomputers. They produce videos of gas flowing, magnetic fields twisting, jets erupting. When the simulations match what we observe in reality, it gives us confidence. When they don't, it gives us mystery. And mystery, in the case of Sagittarius A*, is abundant. For example, simulations predicted a certain pattern of brightness across the ring of emission. But the actual image showed slight asymmetries, unexpected hotspots of radio light on one side of the ring. What causes these? Are they dense clumps of matter falling inward? Are they regions where magnetic fields are amplified by turbulence? Or are they hints of more exotic physics, such as quantum structure near the horizon? To investigate, scientists turn to another tool, polarization mapping. Light can vibrate in different directions. This is polarization. When light passes through magnetic fields, its polarization changes. By measuring the polarized light around Sagittarius A*, scientists can map the invisible magnetic field structures near the event horizon. In 2021, EHT released such a map for the M87 black hole, and now similar efforts are underway for Sagittarius A star. These maps may reveal how jets are launched from the poles of black holes, narrow beams of energy that shoot out across thousands of light years. Sagittarius A asterisk does not currently have large jets, but some believe it once did, or might again. There is evidence in X-ray and radio observations that past outbursts from the galactic center sent shockwaves rippling through space. One such structure, the Fermi bubbles, stretches above and below the galactic plane, glowing faintly in gamma rays. These bubbles may be the fossil record of an ancient eruption, an echo of a time when Sagittarius A asterisk was feeding more voraciously, perhaps devouring a passing star or cloud. We are not just watching the black hole. We are reading its history. And then there are the orbits. Every year, astronomers track the paths of stars near the black hole. These stars, known as S-stars, move in tight, elliptical orbits, some approaching within just a few billion kilometers of Sagittarius A star. Their motions are clocked with exquisite precision using adaptive optics on ground-based telescopes. And as they swing around the black hole, they provide a laboratory for testing gravity itself. In 2018, one of these stars, S2, passed near Periapsis, its closest approach to the black hole. Scientists measured a tiny but crucial effect, the redshift of light predicted by Einstein. As the star neared the black hole, time slowed for it. Its light stretched, shifting to longer wavelengths. The observation was a stunning confirmation of general relativity, right at the brink of a black hole. But other stars behave more strangely. Some appear to speed up, then slow down in ways that suggest invisible companions, perhaps black holes or massive planets orbiting nearby. Others show perturbations that hint at the warping of space itself, possibly revealing dark matter or higher dimensional effects. And then there are the G objects, mysterious blobs of dust and gas that seem to orbit the black hole like stars, but stretch and contract in odd ways. First discovered in the early 2000s, these objects defied classification. Were they gas clouds? Protostars? Some hybrid form we hadn't considered? In 2014, one such object, G2, approached the event horizon. Scientists expected it to be ripped apart, but G2 survived. Its dusty shell stretched, but the core held together. Theorists scrambled for explanations. One hypothesis, G2 is a binary star system hidden in a common envelope of dust, surviving close passes through the black hole's domain like a couple dancing on the edge of a knife. Each of these observations adds to a growing picture. Sagittarius A asterisk is more than a point. It is a dynamic, evolving system. A place where gravity, magnetism, radiation, and quantum mechanics all collide. A forge for mysteries. And even now, with all our instruments trained upon it, we still cannot see beyond the veil. What lies inside the event horizon remains hidden, not just from our eyes, but from our physics. Some have tried to imagine what happens next. Others urge caution, because to look deeper means rethinking the rules. And behind those rules, we may find something waiting, something we have yet to name. When science reaches the edge of observation, when telescopes fail to peer deeper and equations twist into infinities, speculation begins. It is not wild guessing, but an informed descent into possibility. For decades, scientists have tried to envision what lies beyond the event horizon of a black hole, not through direct sight, but through mathematics, analogies, and the uneasy reconciliation of general relativity and quantum mechanics. In the case of Sagittarius A asterisk, these speculations are not idle. They are essential. At the core of the debate is the singularity, the theoretical point of infinite density at the center of a black hole. According to classical general relativity, everything that falls into the black hole is crushed into this singularity. Time ends there. Space ceases to exist. It is a boundary beyond which the universe, as we understand it, no longer applies. But physics abhors infinity. Whenever infinities appear in an equation, it often means something is missing, a deeper theory, yet to be discovered, waiting to resolve the contradiction. Quantum mechanics, which governs the very small, does not tolerate the idea that information can be lost. Yet general relativity, in the context of black holes, suggests exactly that. This conflict, known as the black hole information paradox, has haunted theoretical physics for half a century. In an effort to resolve the paradox, several radical theories have been proposed, each one as mind-bending as the last. One of the earliest is the idea of a wormhole, a hypothetical tunnel through space-time connecting distant points in the universe. If the singularity inside a black hole could somehow be stabilized, perhaps by negative energy or exotic matter, it might form a bridge to another region of space, or even another universe. This is more than science fiction. Einstein and physicist Nathan Rosen proposed a model of such a structure in 1935, now known as the Einstein-Rosen bridge. But wormholes have problems. They may be inherently unstable. Any object attempting to traverse one might cause it to collapse. And the energy conditions required to maintain a traversable wormhole are, so far, purely hypothetical. Still, the allure remains. Could Sagittarius A* be a portal, not to death, but to elsewhere? Another idea is the firewall paradox, introduced in 2012. It suggests that instead of a smooth transition through the event horizon, there may be a wall of high-energy particles, a firewall, that incinerates anything falling in. This challenges the equivalence principle of general relativity, which states that a falling observer should experience nothing unusual at the event horizon. The paradox caused a rift in the physics community, with leading minds taking opposing sides. Stephen Hawking, late in his life, proposed that perhaps event horizons don't truly exist, that black holes are only apparent horizons, and that information might leak out over time through subtle quantum effects. Then there is the holographic principle, an idea born from string theory. It posits that everything occurring within a volume of space can be described by information encoded on the boundary of that space. In black holes, this leads to the notion that all the information about what has fallen in is somehow stored on the event horizon itself, like a cosmic hard drive. Leonard Susskind and Gerard T. Hooft developed this idea, which has since become central to many theories of quantum gravity. If true, then perhaps Sagittarius A* is not hiding information at all. It's projecting it. The interior might not even be necessary, because all the data that matters exists on the surface. And yet, these ideas remain theoretical. No experiment has confirmed a firewall. No wormhole has been observed. The holographic principle is elegant, but abstract, and the singularity still looms, untouched. Other theories explore even stranger realms. Some physicists suggest that black holes might not end in singularities, but in Planck stars, hypothetical objects where quantum gravity causes a bounce, reversing the collapse before infinite density is reached. Instead of a point of no return, the interior becomes a rebounding core that could, over incomprehensible timescales, release its contents in a burst of energy. If Sagittarius A* contains such a Planck star, we may never know. But it offers hope that the universe doesn't simply delete what enters a black hole, but transforms it. Then there are white holes, theoretical opposites of black holes, which eject matter instead of swallowing it. Some speculate that a black hole on one side of space-time could be connected to a white hole on the other, a one-way tunnel from which nothing can return, but through which something might someday emerge. If so, could Sagittarius A* be a one-way ticket to somewhere else? There is no evidence for white holes, but there is intrigue. In 2020, astronomers detected a mysterious burst of energy, a fast radio burst, FRB, emanating from a region not far from the galactic center. Though it was not traced to Sagittarius A* directly, it raised eyebrows. FRBs are millisecond-long blasts of radio waves, incredibly bright and difficult to explain. Could they be signs of quantum processes near black holes? Or even, as some fringe theorists suggest, signals? More conservatively, some believe Sagittarius A* might be a gravistar, a hypothetical object where collapsing matter forms a dense shell instead of a singularity. Inside, a core of dark energy resists collapse, balancing the inward pull of gravity. Gravistars solve some of the problems of black holes, but they remain speculative, with no observational support. And yet, with all these competing theories, there is a quiet consensus among physicists. Black holes are telling us something, not just about matter or energy, but about the structure of reality. They force general relativity and quantum mechanics into the same room, and they don't get along. To reconcile them, we may need a theory of quantum gravity, something that unifies the physics of the very large with that of the very small. String theory is one contender. Loop quantum gravity is another. Each proposes different structures inside black holes. Each offers different outcomes for Sagittarius A star. But perhaps the most radical idea is this: the interior of a black hole is not inside at all. According to some versions of the ADS/CFT correspondence, a principle from string theory, the three-dimensional space inside a black hole might be mathematically equivalent to a two-dimensional surface outside it. In this view, reality as we know it is emergent, a hologram projected from a deeper layer. If that's true, then Sagittarius A asterisk might not be a place at all. It might be a computation, a boundary, a flickering line between states of existence. It is a humbling thought that deep within the center of our galaxy lies not a thing, but a truth. Not a destination, but a challenge. Not an answer, but a question. What is reality? What are space and time? And are we brave enough to follow them into the dark? Let us now imagine, not as spectators, but as participants. What if we could journey into the black hole at the center of our galaxy? Not through metaphor or data or distant telescopic observations, but physically, with a vessel, a crew, and an understanding that the moment we crossed that boundary, there would be no turning back? The concept seems impossible, and yet, scientists and storytellers alike have dared to explore it, not for the sake of fantasy, but for what it might reveal about the nature of space, time, and ourselves. Sagittarius A asterisk is immense. The diameter of its event horizon is estimated to be around 24 million kilometers, 15 times the diameter of the Sun. This scale means that, unlike with stellar mass black holes, the tidal forces near the event horizon are relatively gentle. If a spacecraft approached it, the spaghettification, the vertical stretching and horizontal compression caused by gravity gradients, would not occur immediately. In fact, you might not even notice the moment you crossed the event horizon. No alarms would sound. No visible threshold would announce itself. From your perspective, everything outside would begin to distort, the stars warping into strange halos, time itself beginning to feel unstable. But inside, your clock ticks normally. Your heartbeat continues. The laws of physics, locally, still apply. And then the descent begins. No communication can escape. Your radio signals, no matter how powerful, can never reach home. For the outside world, you have vanished. But inside, you're falling, not in the sense of motion, but of inevitability. Space itself is funneling you toward a future from which there is no escape. You are no longer moving through space. Space is moving through you. If your ship had sensors, it would record odd phenomena. The outside universe would appear frozen, time stretched to infinity. The starlight behind you would become compressed, bluer, hotter. The starlight ahead, if such a direction exists, would stretch into red, fade into black. Eventually, all things outside would fade into silence. But what would you see inside? In theory, you would continue falling toward the singularity. But as we've explored, many physicists now believe the singularity is not a point, but something else, something structured by quantum effects. Some theories suggest you might encounter a region of high energy, dense but not infinitely so, where particles behave unlike anything known. Perhaps you pass through the firewall, if it exists, and are incinerated instantly. Or perhaps not. Maybe you fall into a region where the laws of causality break down. Past and future blur. Events become nonlinear. You encounter echoes of your own motion, light reflecting from inside the event horizon, bent by extreme curvature. You might see the universe's entire future played out before you in a compressed window of time. Or none of it at all. But let us continue imagining. What if, instead of a crushing singularity, you encounter a bounce? A Planck-scale core where gravity and quantum pressure balance. In this moment, the collapse halts. You feel the change, not in physical pressure, but in the structure of space around you. The inward funnel twists. The geometry flips. And you begin to move, not downward, but outward. Are you now in another universe? Have you emerged through a wormhole? Or have you simply ceased to exist? There are models that suggest you might exit into a region of low density, a white hole that expels all matter and information in a radiant burst. In this scenario, your journey becomes part of the larger cosmic cycle: collapse, bounce, expansion. A loop of creation and destruction, endlessly folding space into new forms. Other theories are less kind. Some suggest your consciousness, your identity, ceases long before anything happens. The descent, while smooth on paper, ends in thermodynamic chaos. Atoms ripped apart, information scrambled, and space dissolved into meaningless gradients. You don't travel. You are erased. But still, some hold out hope. Because if black holes store information, if the holographic principle holds, then perhaps what you are, what you've seen, and what you've known is never truly lost. It becomes part of the black hole's quantum fabric, encoded in surface vibrations, spin states, or gravitational echoes. You become a pattern woven into the most mysterious object in the galaxy. A whisper in the dark, Sagittarius A*, then becomes a storyteller, a keeper of lost voyages, vanished explorers, consumed stars, and forgotten signals. It is a library of gravity, its volumes written not in ink, but in curves, waves, and fields. And what lies beyond? That, perhaps, is the point. Because the question isn't just what's inside the black hole. It's what kind of universe makes such things possible. What kind of reality allows for objects that end space, stop time, and store infinity behind a veil of silence? Maybe Sagittarius A* is not just an object. Maybe it's an invitation to explore, to question, to imagine. And as you float, weightless, in the thought experiment of falling into a black hole, you realize this. The value isn't in reaching the center. It's in the journey inward. Because even if we never cross that final threshold, we've already passed another, the frontier of understanding. And behind us lies a universe forever changed by the act of wondering. The stars are quiet now. The instruments have gone still. The silhouette of Sagittarius A* remains, suspended against the chaos of the galactic center, unchanging, unknowable, and yet strangely familiar, like a memory we've never had. So let us leave it there, gently, in the dark heart of the Milky Way. A cosmic question mark. A gravitational pause. Somewhere, far from Earth, a signal drifts. A photon escapes. A flare rises and fades. And perhaps, just perhaps, a new eye opens to peer once more into the abyss.